you what is your IXX. So over here, your IXX is equal to, so this is your IXX, 40.8 times 10 to the power of what? Minus 6, because that is plus 6, you change to meter. Now, a lot of times again, the same thing, same issue that we all face is what is our y distance, right? So that is our, so we have to multiply by y. So this is our y distance, right? This is our y distance. Wait, see, even I'm confused. Yeah, that is our y distance, because this is our y-axis, that is our y distance. So the y distance is d divided by 2, right? So d over here is, we found out that the depth is, on this one is 205, so it's equal to 0.205 divided by 2. And we know that it's going to be what? Tensile. Okay. Then the next one, we look at your my. All right, we look at your my. So we start looking for my. Right, my. Okay, so for element A, my is going to be under what? My, we analyzed earlier. My is going to give us compression. So we put down here. So now this is plus. Then minus is going to be compression, 9600. Right? Divide by IYY. So you look at the table, look at IYY. Right? So it's 9.03 times 10 to the power minus 6. Right? Then is your, sorry, I got this wrong. This is my x distance. Okay, then you have to find out x distance. So this is our x distance now. Right? I'll use a different color. So this is our x distance. Right? So our x distance, so we know from our problem set, if we look at our problem set, we are aware that x is from the tip 0.75 millimeters. So from here to here, we are given that this is 75 millimeters. And the BF, yeah, your best friend, your BF over here is 166 millimeters. Okay, so this distance over here is what we want to find. Okay, so that distance will be equal to 0.166. So that distance is equal to 0.166 divided by 2 minus by 75 times 10 to the power minus 3. Okay, so that is your solution, right? So from here we start calculating this out. So this will be equal to 100 divided by 5320 power minus 6 is equal to 18 point, so it's minus 18.797 times 10 to the power 6 plus by 22750 times by 0.205 divided by 2 divided by 40.8 power minus 6, 57.154 times 10 to the power 6, and then minus by 0.166 by 2 minus by 75 power minus 3 times by 9600 divided by 9.03 power minus 6 is equal to 8.505 minus by 8.505 times 10 to the power 6. Okay, so this whole thing will be equal to minus 18.797 plus by 57.154 minus 8.505 is equal to tensile 29.852, right, times 10 to the power 6. Pascal. Okay. So this is what we have calculated. Now, some of you will ask Eugene, what are we trying to achieve down here? Okay, I'll tell you. So if we look at, but before I go on, are you all clear? Yes or no? Are you all clear about the analysis? Right? You guys have seen all of this before, yes or no? In the first 3 weeks of the lecture when we did bending stress. Anyone, any questions so far? I hope you are still there, okay, not sleeping. Right? I hope so. Right. So from here, right? So from here, what we are trying to achieve, okay? So we are trying to calculate stresses on element A based on the transformation that we have. So if I were to draw element A, okay, so this is my element A in 3D now. Okay, so this is element A. So element A, based on the transformation that we're given, this is my X, this is my Y, and this is our what? Our Z. So what we have calculated now, okay, what we have calculated now is we have a normal stress in stress Z, right, which is equal to 29.852 megapascal. And this is induced by axial load, moment in the about the x-axis, okay, and then moment about the y-axis. So this is what I've done. Okay, so what we want to find out is do we have stress X and do we have a stress Y? So from how our structure has been loaded, okay, so from how our structure has been loaded, okay, so I'll teach you how to analyze this later. We realize that stress X and stress Y are equal to 0. So if you look at the normal stress, if you look at our problem on our right on our right column now, yeah, my computer is really slow. Normal stress in the X direction, you don't have any normal stress, right? The 8 kilonewton that you see down here are not going to induce normal stress, are going to induce stress. Then in the Y direction, the normal stress is equal to what? 0 also. Okay, so that's why I specify stress X and stress Y. So the next thing that we're going to look at is we're going to find out, do we have any shearing stress? So the shearing stress that we're going to calculate down here, so this is for element A. Okay, this is for element A. Now don't switch off, okay? I know now it's like, oh no, we're not going. Don't switch off, okay? When things get complicated, you keep your brains alive. Don't give up, okay? Don't like, oh, here we go again. Don't switch off, okay? This is this part that we can earn a lot of money, okay? So if you don't use analytical calculation like this, you have to use finite element. Okay, that I hope you guys will take in your upper years. The problem with finite elements, to analyze a structure like this, the software is about $300,000 to your company. Okay, most companies don't buy them unless you're working in very big corporate company. So we are still going to rely on fundamental calculation like that. That's not worth $300,000, but maybe it's your salary that's going to be $300,000. I'd rather you get paid $300,000 than your company buying a software $300,000 annually. It's not cheap, okay? Right. So if you look over here now, so we're going to calculate. So if you look over here, we're going to determine our stresses, shearing stress, X plane, Z direction, and this is equal to shearing ZX. Okay. So next, we are going to look at our shearing stress next. Okay, so I'm like, oh no, shearing stress. Okay, so that's what we're trying to find. Define the stress state of the element. Okay. So what you can see down here, the normal stress, some of you like easy peasy. I can nail this down really quickly. Yeah. The shearing and the normal stress is always the easy part. Now, on top of that, I'm gonna bring you on top into what? Into shearing stress. You guys say, oh God, here we go again. Okay, so we're gonna look at shearing stress now. Right. So I'm still going to we're going to find. Okay, so we're going to find the shear XZ, okay, generated by Vx. Okay. Okay. So we also on this structure we're going to use thin wall analysis. Okay, we're going to apply. I'm going to declare this. We're going to apply thin wall analysis. Okay, we're going to apply thin wall analysis. So over here, we start by looking at our, I'm going to copy our structure again. Okay, I hope to locate my mouse. Okay, so there is our structure. So we are going to find, so if you go back to our analysis, right? So we want to find our Vx, right? So Vx is running at our 8 kilonewton, okay, per side. So this is our Vx. So this is our Vx. So our Vx we found is 16 times 10 to the power 3 Newton, right? So we find the position of our Vx. So over here, our element over here, this is your element A, right? This is your element A. Right, so the formula that we're going to use is going to be equal to shear XZ is equal to Vx, right, over Iyy. First moment of area about y-axis divided by the what? Thickness. Okay, so there is the formula that we're going to use. Right. So Vx we know, right? Iyy is equal to, so Iyy, because the shear force is acting perpendicular to the axis, right? To this axis over here, right? So this is your shear force. So it's about a y-axis. So you look at Iyy. So our Iyy value is equal to 9.03 times 10 to the power minus 6 meter to the power 4. And then always the killing part is your what? Is your Qy. What is this Qy? Right? Right? It's like, after you do so much, okay, this value, so thickness, okay, later on we talk about thickness, or in fact, we can solve the thickness. So this is the thickness that we're interested in. Okay, and this is equal to the thickness of the what? Of the flange. So you look at thickness of the flange is equal to 11.8. Okay, it's equal to 11.8. Is it 11.8? Yep, 11.8 times 10 to the power minus 3 meters. Okay, that's the thickness of the flange. So now when you look at this, you know your Vx, Iyy here. or you know your T, right? So this is the part that you don't know, right? So it's thin wall analysis, right? Your Vx is going here. You're going to sketch your shear flow.